Okie dokie. Let's talk about things stochastic. I think that what we'd like to do probably is to start this out with any global questions that you have concerning the take-home test. And hopefully you've been able to start from it, and it'll be due 1 week from today. So let me share my screen, and let's see what pops up. Okay, I do have it on here. So one of the things that I'm willing to do is to talk about any elaboration that you would like on any of this. 25th, March 30th. Okay, we're going to make this due on March 30th, right?
I have a question about number 3.
Okay, number 3. Let's talk about number 3. Yes.
Okay. So I'm looking through our notes, and we use I think it's called Leibniz rule.
Yes, right.
And in the examples that we did, we were able to basically constrain the relationship between our random variables to a geometric region. And
Well, to a what now? A geometric region.
yeah, for instance, one of them we constrain it to the line, to the area below the line y equals x, or it might have been y equals minus x.
Okay.
And this is a little bit more complex of a function because we're not just doing the product of two random variables. Should we still be trying to find a geometric region over which?
Yes, the answer is yes. You should work this the same way that you work the min, the same way that you worked x times y. And you'll notice I've made it a lot easier because we started out with the random variables, both of the random variables being IID and uniform on 0, 1. And that's going to help your result a lot because all of your probability mass is over the unit square. So anything you integrate over, you're just going to integrate over the unit square. So does that help?
Yes, that does help. I wasn't thinking about it as a unit square. And
yes. Yeah, so that's the way we started it out. And I think you could probably do this for all of the probability mass in the first quadrant also. But this makes it a lot easier and makes the integrals that you're going to have to do a little bit more palatable. Okay.
Thank you.
And I should have put in there, I just did assume that we know the joint probability density function for X and Y. So anything that you given well, you know what? No, I don't have to do that. We're already given the, I did that prematurely. We're given the joint distribution of X and Y right here in the beginning because we know they're IID on 0, 1, right? So we're given the joint density already. I don't have to explicitly put that in there later. It's given implicitly, I guess. Okay, any other comments at all? Or any other questions? Okay, well, this means that you have a good hook into the problems. Please, by the way, just do one problem per page. Okay, don't try to squeeze everything on a single page. I would appreciate that. And if it's an economic disadvantage to you, I will pay for the extra paper if you use paper. Okay. Okie dokie. Well, this is good. This means that because these are not straightforward generalizations of stuff we've done. You have to do a little bit of thinking above and beyond. This, without elaborating, did anybody get the first one yet? Okay, wow, Matt got it. Okay. And this one is very interesting and requires you to combine a couple of things that you saw previously into a single solution. This one we just talked about. Let x and y be IID, and z is equal to y raised to the 1 over x power. I chose this because the math looks a little bit more difficult. But you know what? It turns out to be easy if you grasp the math very well. And then find an example of equality for okay, and then derivation of the chi-squared random variable. You might be able to find this online. I'm not sure if you're able to find the derivation online. That's the reason, like in B and D, I said compute the corresponding characteristic function. In other words, I want to see your derivation, not just looking it up on Google or something like that. Okay, well, that's all well and good. Let me go then to the lecture, and let's see what good things we have from last time. We talked about the chi-squared, and then we're going to talk about optimal betting, I think, today. And this is something that you all want to know. Now, the interesting idea here. Okay, I'm going to mess around with you on my screen and just have this. Okay, these are multiple random variables. It's a gambling sequence. This is an application of the law of large numbers. And here's the idea. The idea is you play a sequence of Bernoulli games. And here's something to remember, gentlemen. If your probability of winning is less than a half, there's no way that you can, there is absolutely no way that you can win playing multiple games. You will lose. So in order for this to be applicable, your probability of winning has to be greater than 1/2. So if it's less than 1/2, you will lose everything. If it's equal to 1/2, it'll be kind of a random walk, and you don't know which way that it'll go. And here's the problem. You start with a stash of D dollars. So I'm going to do a little bit of abusive notation here. So you might start with something like, for example, $100, or maybe even $1,000. And if you bet and lose, you lose what you bet. So if you take out of this $1,000, you bet $50. If you lose $50. If you win, your stash becomes $1,050. If you lose, it becomes $950. You get the idea? So whatever percent you bet, that's either added onto your stash or it is subtracted from your stash, depending on whether you win or lose. And the question is, what is the optimal percent? What we're going to do is we're going to assume that we have a stash. We have a stash of D dollars, and whatever stash is, we're always going to bet the same percent. So we might always bet 10% of the money we have available. We might always bet 50%. And I think, as we said last time, you don't want to bet 0%, because if you bet 0%, you're never going to win anything. And if you bet 100%, you lose the first time, you're out of the game. So notice with this percent bet, you're always in the game. We're going to assume that everything is fractional, so we can go down to fractional pennies, if you will. So you'll never be out of money, because you're only going to bet a percent of what you have available. Okay, so let's go with this. And we're going to start with an example. The first example sequence is you win. And what you do is, this is the amount of money that you bet. You bet the percent of your stash. So if you win, your new percent is your new stash is equal to D plus the percent of the stash that you won, under the assumption that you win. So your new stash at the end of 1 is equal to 1 plus this percent. This is a variable. We're using this as a variable like X. Okay, so that's well and good. What happens next? If we lose, we're going to take our previous stash, this D1, and if we lose, we're going to have a new stash of minus the percent of D1 that we bet. So if we look at everything and combine it with this top equation, we get that the result is this. It's 1+%. This is because of one win, and 1 minus the percent. This is because of one loss. You know what? I think I misspelled lose there, didn't I? Did I misspell loose? I think I did. I think you spell lose, L-O-S-E. This is loose. So, oh well. D3, let's suppose that you lose again. Well, your new stash is going to be equal to your previous stash, D2, minus the percent that you bet of D2, which can be written as this. We start to see a pattern emerge. This is one win, and this is two losses. So we see that every time we have a win, we raise this to another power. And if we have a loss, we raise this to another power. We have two losses, so this is raised to the second power. So we begin to see a pattern there. And then if we win again, I think you can see what happens. We have two wins and two losses. So both of these terms are to the second power. So we're well and good. And therefore, we can look at this and we can kind of generalize that if we have n trials and k wins, this sounds a lot like a binomial random variable, right? K trials and k wins, this leaves us a stash of the number of wins raised to the power of 1 plus the percent that we do, times 1 minus the percent of all of our losses, times your original stash. And so this is the way that the percent goes. So what we'd like to do is we would like to find a percent that maximizes how much money you make asymptotically. As n gets very, very big, we would like to maximize this. So here's what we're going to do. This is the exact same equation of the previous slide. And then what value of percent maximizes d of n for large values of n? What percent should you bet? Now, here's the thing. If you have a function, say you have a function, let's see, x of t or x of n. And I'm going to draw this as a continuous random variable, and you maximize this. And then if you raise this to I don't know, to a strictly increasing function, let's say e to the x of n. So it's the same result. This will be a little bit different function, but you know what? Because this is strictly increasing, the maximum here will be exactly the same as the maximum here, as long as the function that we talk about is strictly increasing, and e to the x is strictly increasing, right? So we can take any function of this random variable, any strictly increasing function, and maximizing x sub n is exactly the same as maximizing the function of x sub n if the function is strictly increasing. So it's the same as maximizing 1 over n times the log of d sub n. And you'll notice the log of d sub n, the log function goes like this, right? So it's strictly increasing. So maximizing b sub n is the same as maximizing this. So this d sub n is the same result that we have up here. So we're going to take this, we're going to substitute it here and take the logarithm of it and recognize that maximizing b is the same as maximizing d. If we take the logarithm of this equation on the top, we get the equation on the bottom, right? It's k over n times the log of this first thing plus n minus k over n times the log of the second thing plus the log of d. And so how do we maximize it? Well, we go back to freshman calculus and we take the first derivative and set it equal to 0. Before we do that, however, we're going to recognize some results. or we're going to recognize and apply some law of large numbers. If you have a bunch of bets and you take the limit of k over n, that is going to be equal to the probability of p. That's a result of the law of large numbers. For example, if you take the limit as k goes to infinity of the number of, I'm going to do a dice, say the number of 3 pips on a dice, divided by the total number of rolls of the dice, that should be equal to 1/6. If you roll these dice enough, you're going to get 3 pips 1/3 of the time. So this is something we're going to apply. The law of large numbers apply, and we can make this substitution that k over n is equal to 1 over p. Well, that wasn't very good. I I wrote over my next equation. So n over n minus k over n, that's going to be equal to 1 minus k over n. And so this is going to go to p. And so the limit of n minus k over n goes to 1 over p. The other thing that we're going to do is to make this substitution. And if we make this substitution from the previous equation, we can say that the law of large numbers is going to get p times this logarithm plus 1 minus p times this logarithm. Previously, this was n over k, or no, k over n. I'm sorry, this was k over n, and this was n minus k over n. And so this substitutes here, and this p substitutes for this. So now we get to the freshman calculus. I jumped my gun. Now we have to go to the freshman calculus and take the first derivative and set it equal to 0. This is kind of interesting because the first thing we notice is this log of d goes away. And this says that the percent that you bet is independent of your initial stash. If you think about it, that makes a lot of sense, doesn't it? That that the percent that you bet is independent of your initial stash. So when we take the derivative, this part goes away, and we're left with this result. And we need to set that equal to 0, and solving for it says that the maximum is 2p minus 1. That's what you should bet. So if you have, for example, if you have a 60% chance of winning, then you should bet every time 1.2 minus 1, which is 0.6 times 1, you should bet 20%. 20% of your stash every time if your chance of winning is 60%. And that will maximize your winnings. And that's the result. Twice your probability of winning, minus 1. Notice some interesting things. What if p is equal to 1/2? What's your optimal betting?
Not betting at all.
You're not betting
So
at
it stay
all.
the same.
Yeah, your percentage is 0. And what about if your probability is like 1/4? Well, this is kind of weird. It says that, let's see, percent is equal to minus 1/2. So you should bet minus 1/2 of what you have, which is stupid because you can't bet a negative amount. What if p is equal to 1? What does that mean? P is equal to 1 corresponds to you winning every time. If you win every time, what is the percent stash? What should you bet? You should bet 100% of your stash every time if your probability of winning is equal to 1. So all of these match, if you will, kind of a sanity check. They all match a sanity check. So this is kind of cool. So if we place this result into the original equation, this is the original equation that we started out with. And this was the equation before we took the log and stuff like that. And what we're going to do is we're going to take the percent and substitute 2p minus 1. And this will tell us how much money we have if we optimally bet after n times. And the amount that we bet after n times is given by this relationship, substituting the 2p minus 1. And then we're going to take the nth root of that because this tells us what happens after, well, this is going to be a useful result. So if we take this number raised to the 1 over nth power, we get 2. This is kind of interesting. P to the p and 1 minus p to the 1 minus p times d to the 1 over n. And this turns out to be a useful metric that we can do. And we've just gone through the sanity checks, so we're good here. So what this does is that d sub n over d is equal to this relationship. So d sub n, remember what d was? D was your original stash. D sub n is what happens if you your stash after n plays, and the number of turns to double your stash. This is your double time. This is how many times you have to play to double your money. What do we want d sub n over d to be? We would like this to be equal to 2, right? If d sub n over d is 2, n, if we solve for n, that would tell us how many games we have to play on average to double our money, assuming the law of large numbers is kicked in. So the result of that, solving for n, is that n double, this is the number of games that you have to play to double your money, is given by this expression. Now, this expression is kind of cool, but it's lost all personality to me. I don't understand what's happening here, other than that I followed the rules of the algebra and elementary calculus and applied the law of large numbers and got this result. And this is what the double numbers are. And so this is n double, if you're interested in it. This is the number of games that you have to play to double your money. So let's look at these different results. You'll notice, first of all, p has to be greater than a half. So we don't have anything here greater than a half. But say that you win, you want to double your money in 5 turns. It looks like on the average, if your chance of winning is 75%, you're going to double your money every 5 turns. And you can see the closer we get to 0.5, for 0.6, we have to, I don't know, this looks like 34 times. It's going to take us longer the smaller our probability is. The closer we get to a half, the more games we're going to have to play. And out here, we see that if the probability is equal to 1, okay, if probability is equal to 1, trying to draw a dashed line over here, that this turns out to be 1. So if your probability of winning is 1, you double your money every game, right? It just takes you 1 game to double your money. So this all meets the sanity curve. So in the end, this is the law of large numbers associated with winning. Yeah, p is equal to half, n is equal to infinity. Let's look at this. That's another sanity check. For p is equal to a half, this turns out to be 1/2 times 1. Is that right? P is 1/2 log, oh, it's equal to -1. And over here, okay, so this is equal to 1. This is n double for p is equal to 1. And of course, this is going to be 1 over infinity, or 1 over 0, which is equal to infinity. So if you have a probability of 1/2, it's going to take you an infinite number of times to double your money. So all of these meet kind of sanity checks and give us give us a result that kind of makes sense. And at p is equal to 1, as we've already pointed out, the number of times to double is just equal to 1. So let's look at this. Let's look at a very interesting case of roulette. This is a standard roulette wheel. And if you recall, you can bet on even, or you can bet on red, or you can bet on black. That's basically betting on a one or an odd number. It's like betting on an odd number or an even number. But if you just bet it on odd and even numbers, that would give you a 50-50 chance of winning. So what they do on the roulette wheel to put the odds in the favor of the house, they put a 0 here and a 0 here, which is neither odd nor even. But if we make a bet on even or green, it turns out that there's 36 results here on the edge of the wheel, and that even or green is 20. So that makes your chance of winning at roulette, if you have even or green. Don't forget that probability has to be greater than 1, and even or green makes it greater than 1. It makes it 0.5557. And the percent that we want to bet is twice this amount minus 1, which is 11%. So every time you bet about 11% of your stash on even or green, and it will take you 111 or 112 games to double your money on average. Okay, so this is an application of the law of large numbers, if you will, applied to roulette. And there's another interesting question. Now, before, you lost all of your money. You lost the percent of your money. What if you just lost a percent of of what you bet? In other words, if you bet $10, you might not lose $10. You might lose $5, or you might lose $20. It depends on what that value of L is. And the same thing for the winning. Instead of just winning what you bet, you're also going to be able to bet, you're going to get back W times that. So if you get back a point, I don't know, if you bet 20%, and W could be, you get back twice what you win. So you might get back twice the percentage that you bet. Now, we're going to assume that L or W can't exceed 1. And the question is what is the optimal betting then in that case? I'll be assigning this as a homework in a subsequent class. Okay, any questions at all? Okay, this is interesting. So now you know, if you go to Vegas and you're in a game where you can win the game, you know that indeed you bet twice the probability of winning, if you know the probability of winning, -1, and that's going to optimize your returns in the long term. An example of the law of large numbers. Okay, here's another example, and this is very interesting. The next example I'm going to use is something, or I'm going to present, is something from the law of large numbers that has to do with stochastic resonance. Stochastic resonance. Stochastic resonance is something which occurs in nature and is in biology, wherein you have an animal who one of their senses works very well if there's background noise. It works very well if there's background noise. Now, what's an example of that? One of the examples is, I believe, a crayfish, or a crawdad, as they call in Louisiana. They have a stochastic resonance which takes into account the sound of the water running in the brook. And there's always water running in the brook, and that's noise, right? And the crayfish has a sense of when it gets attacked, that they have to detect a small signal in that very noisy environment. And what they do is they detect a sinusoid, because if you think about, say, a fish, for example, swimming towards it, or another animal swimming towards the crawdad, they're going to have to move their feet or their gills or their whatever, their fins, in order to move towards the crawdad. And that's going to generate a very weak sinusoid in this very noisy environment. Well, it turns out that the crawdad has a sense that if you have some background noise, that their detector works perfectly. However, if you take away that noise and you put that crawdad in still water, its detection will not work as well. Or if you have too much noise, it won't work as well. There's kind of a golden point in there where you have this resonance, if you will. So if we talk about the probability of detection of an attacking thing, it's going to be, as we look at the amount of noise, it's going to peak at some value of the noise. So that's interesting. Now, similar, believe it or not, a similar sort of thing is a camera. Imagine that you have a camera that every time you take a picture, we're going to talk about a black and white picture, every time you take a picture, it just takes a black pixel or a white pixel. Is that okay? A black pixel or a white pixel. Now, whether the pixel is black or white depends on the gray level. Say that the gray level is between 0 and 1. This camera is going to take a photograph so that if you are, say your gray level is 0.6, there will be a 60% chance that that gray level is black, that the camera takes a black, and 40% that it gives you a 0. Does that make sense? So you take a picture, and again, every time the camera can just detect a black pixel or a white pixel, but it does it randomly. And the randomness is uniform depending on what the gray level is. The smaller the gray level is, the greater the chance it will choose a value of 0. The larger the gray level is, the darker it is. Did I get my blacks and whites mixed up? I did. 0 is black, 1 is white, right? Okay, so sorry about that. So the closer it is to 0, the closer the probability that it will be black. The closer it is to 1, the greater the probability it will be with white. Does that make sense? So you take this picture, and you can imagine doing this, just taking your gray level and go through it by pixel, using a random number generator and generating this binary black and white pixels. But here's the interesting thing, that is going to be repeated. So we're going to take a picture of this black and white. Then we're going to take another picture with the black and white using totally new random variables, same probability distribution function. You get the idea? So we're taking a number of pictures of black and white images. Each one is going to be independent of the other one, but each one is going to choose a black if the pixel value is close to 0, and it's going to choose a 1 if it's closer to white, and it's going to choose it probabilistically in accordance to whatever that gray level is. So a 0.6 gray level is going to choose 0.61, and it's going to choose 0.40. And we're going to go through all the pixels like that, and we're going to take a number of pixels. So we have this terrible, terrible camera that only takes black and white images. Yet we are going to take a number of them, and we're going to generate a number of pictures, each one of which is a different random instantiation of the same random variable. I don't know why I have that there. Okay. Do you kind of get the idea? Okay, if you don't get the idea, let me see if I can share this screen and kind of give you an idea of what it's supposed to be. Okay, here's the idea. This is a picture of a guy I used to work with. named Bob Miyamoto. And you can see, Bob, this is a nice gray level image here. It's a nice gray level image. So what we're going to do is we're going to take one of my pictures where each one of these pictures goes white or dark in accordance to the gray level. And the probability of going dark or white, black or white, is going to be dependent on the pixel value level with a uniform random number generator. So what we have here is this, the third one over is more like the sort of image that we would get. These other ones are just kind of jokes. Now, here's the point. If I take a picture like this and I take another picture like this where the gray levels change, but in accordance to the same probability, what is going to happen? First of all, we have to figure out how we're going to threshold the image. And you can see here, as on the top, stochastic resonance is loosely defined as the phenomena in the detection process where the addition of just the right amount of noise improves performance. Too little or too much noise is a degrading performance. So here's a picture of Bob Miyamoto. Okay, what I'm going to do, and this turns out to be very interesting, is to first of all do a threshold. I'm going to do a straight threshold across here. And you can see that it doesn't look like Bob Miyamoto. Everything above a 0.5 is 0. And I'm sorry, everything above a 0.5 turns out to be a 1, a white. Everything below turns out to be a 0. So you can see the background here is below 0.5. So this all comes out as white. Bob's hair, which is black, stays black, and you can see that some of the darker areas remain darker. Now, here's the interesting idea behind the stochastic resonance, which is equivalent to what I talked about before. We're going to add some noise to the random variable. We're going to add some noise to the image. So each pixel has a random amount of noise put into it, and this is a uniform amount of noise. It's a uniform amount of noise. So here we put a little bit of noise in here, and now we threshold it again. So we've added noise to this picture and we've thresholded it again. Here, we've added a little bit more noise and we've thresholded it. I want you, as you look at your screen, to try and squint. I'd like you to look at your screen through a squint, because your squint literally performs a low-pass filter, and see if you can tell me which one of these, this one, or this one looks like too much, looks like Bob Miyamoto the best. Now, I don't know about you, but if I squint, I can see Bob Miyamoto's eyes. I can see his eyes here. I can see him in this picture. I can just make out his eyes. But over here, I don't see his eyes. But again, you have to squint to see that. Does that make sense? And so here we don't have enough noise. Here we have too much noise. And if your eyeballs work the same as mine and you squint to look at Bob Miyamoto, you should see that this looks to be just the right amount of noise to recognize Bob Miyamoto.
I have myopia, so if I remove my glasses, it works pretty well.
Oh, is that right? Okay. Yeah. And squinting helps too. And do you agree with me? If you squint, you see this one a little bit better?
Yes, I agree.
Yeah, okay. So I've blurred them a little bit so you can see it better. I've taken this picture and I've just run a smoothing filter over it to smooth out the high resolution pixels. And so this is the original picture. This is blurred. This is the original picture with just no noise. This is with too much noise, and this is just right. And I think with the blurred pictures, you can see that, yeah, there's more information about Bob Miyamoto here than there are in the other places. Okay. So this is all well and good. So if we do dynamic stochastic resonance, we do the following. And unfortunately, this is not going to be as fast as I wanted to. I've tried to do faster simulations, but I've never gotten around to it. We're going to take this picture of Bob Miyamoto here. I guess I can play it. No, I guess I can't. We took this picture of Bob Miyamoto. Now we added random noise to it and thresholded. Suppose we added new random noise to the same image and thresholded it. Added new random noise to the image and thresholded it. What would happen? Well, if I go to full screen here, you can see what happens. Now, ideally, what would happen is that you would see Bob Miyamoto here more clearly. And again, if you squint, or if you're like Glauco and take off your glasses, you can see Bob Miyamoto a little bit better in the center picture, than you can here. And clearly, since there's no noise added here, you can't see Bob Miyamoto at all. So you get the idea? This one is, that one's too little noise. That's too much noise. This is just right. That reminds you, of course, of the Goldilocks nursery story, not the nursery story. Yeah, the old child story. Now, what would happen instead of trying to do this and hoping my eyes would integrate? I was kind of hoping my eyes would integrate over time. And if I saw a bunch of these images back to back, that my eyes would not be able to respond fast enough and I would see it kind of blurred with respect to time. That didn't work too good. But what happens if we take a number of these images and literally take the average of them? And this is going to be the threshold that we use. And I'm not going to go into this too much. I'm going to present this mostly heuristically. And here is the result that we get. Here is an original image. And here is uniform noise. In each case, you add uniform noise and you threshold at alpha. Well, alpha is equal to 0. Nothing happens here. This is alpha is equal to 2.5, 0.5. And you can see as I begin to average these images upward that if I have too much noise, if I add too much noise, then it doesn't work. What the alpha is the standard deviation. I'm adding noise, which looks like this. I forget. I think it's just one-sided. No, it's two-sided. So I'm almost certain, if I remember right, I'm adding alpha here, and this is the random variable of the noise that I'm adding, and this goes all the way to 1 and -1. And unfortunately, I don't remember if this is one-sided or two-sided. Sorry, guys, I did not prepare well for this. So if I added alpha is equal to 0, which means that distribution had 0 width, then no noise would be added. If I added a little bit more noise, 0.25, so the density function of the uniform random variable is 0.25. If I chose 0.5, I get this. And this is 0.75. Alpha is equal to 1. And this is alpha is equal to 1. So this is uniform noise, which is really broad. So it's taking those pixels and whipping them all around up and down. And this is even more noise with alpha is equal to 1.5. So you can see that looking at this is kind of a toss-up between if you just with your eyeballs, it's a toss-up between 0.25 and 0.5, right? But it turns out that the 0.5 is indeed optimal. Let's see if that carries out in the next result. This is a picture, and this is the original picture. So if I just add noise to the original picture and I threshold it at 0.5, or not threshold, but I take an optimal amount of noise and add. We determined the optimal noise on the previous slide. Now we're adding the optimal noise in all cases. If I add the optimal noise and I And I just take one picture, that optimal noise threshold, it looks like this. This is with it, you can see averaging 8 of these, averaging 16 of these, et cetera, all the way up to 1,024. So this is with 1,024 instantiations of this. Now, what's happening here? Well, since the noise turns out to be proportional to the gray level, in the end, the average approaches the mean. And what's the mean? The mean is the gray level. If we add just the exact amount of noise. And so we can see the law of large number is applied here. And this lets us see that if we had this terrible camera that just took black and white pixels, and we could arrange noise in this camera in an optimal way, that we could literally take very high precision gray level images just by averaging a number of these noisy images together. And the noise has to be just right. If the noise is too big, it doesn't work. If it's too small, it doesn't work. It has to be just exactly right in order to get this reconstruction. Here is another example. And this is just a gray level. This is with no noise. This is with alpha is equal to 1/4. So here, what we're doing, let me show you. Here we did from here to here using the same noise. So what I'm going to do is I'm going to give you a number of examples now going from here to here, and I'm going to skip all the intermediate results. I'm going to skip all the intermediate results to just give you the end result, showing what happens if you don't add exactly the right amount of noise. So this is an original. This is using alpha is equal to 0, corresponding to no noise. This is equal to alpha is equal to 0.1, or is equal to 1/4, which is just a little bit of noise. This is alpha is equal to 1/2, which is a little bit larger. Alpha is equal to 3/4, which is a little bit bigger here. And then alpha is equal to 1, which is the most noise. Now you notice we're up against kind of the limitations, because if you put too much noise and you get a pixel value greater than 1, we're assuming the pixel values can go from 0 to 1 here. If you get a pixel value greater than 1, you have to round it down to 1. And if you get a pixel value less than 0, you have to round it up to 0. So that takes into account the kind of poor contrast that occurs here. And you notice it kind of looks like, yeah, this is more of a high contrast photo. This is perfect. This is perfect in the sense that it matches the original. It's hard to tell the difference between this image and this image. They look almost exactly the same. But clearly, if you compare with the original image, the other ones don't work in the stochastic resonance. So this is an example of where you can add noise and get exactly the results that you want. And it makes use of the law of large numbers. So that's another example of the law of large numbers. I'm not going to go through the math, but I think that my heuristic explanation should be sufficient. Are there any questions at all? Isn't that interesting how you can use noise to get high resolution out of low resolution? Theo in the car.
Yes. Do you know if that type of algorithm, or we are using noise and then like basically getting back the original image from that noisy like starter, do you know if that's actually used? Like if, because the cameras have at some level a certain amount of noise inside of the sensor. Do you know if that's something that is actually used?
No, I don't.
Or can be used?
No, I don't believe it is. I don't believe it is.
Okay.
I do know that this idea of stochastic resonance does occur in nature, like I talked about with the crawdads, and is presented usually at a higher level than I presented it. In fact, I saw originally the idea of stochastic resonance displayed as the solution of a stochastic differential equation. Ooh. And this idea popped into my mind, and we wrote it up and published it. It was, I think, a very elementary example using the law of large numbers. So no, I don't believe that any cameras use this. But that is that, you know, that's well, that's interesting. You have a photon detector that measures photons coming in, and these photons are going to be very noisy. What do you do, like in radiometers, where you're trying to look at a star which is far, far away, so far that you get some photons coming in, right? You get some photons, and you use the law of large numbers to just accumulate the photons. There is no additive noise right there, but that's another example of kind of a histogram being a, well, yeah, the histogram is going to give you the overall arching. That's another example of the law of large numbers. It's going to give you the image. It's not related to the example we gave here, but I think that that's another case where you use this idea of randomness and the law of large numbers in an applied area. Okay.
Neat. Thank you.
Okay. Any other questions at all? Okay, I hope these were just kind of fun examples of the use of law of large numbers. And again, the idea is the law of large numbers says that the mean approaches the average, or more in general, as a function of x approaches the expected value of the function of x. For example, let me go to a whiteboard here. Oh, I guess I was messing around here. Okay, the idea, say you had a number of values. Okay, and then you had arbitrary functions such as g of x. So this is data that you're accumulating. So g of x, I don't know what, I'm not even going to make up g of x. Okay, what I've done is I've rounded x down to the nearest odd number. Why not? Why not? It can be any function at all. So we know that if we sum these up and we divide by n, that we're going to get something which is very, very close to the expected value of x, right? The law of large numbers is also applicable to g of x. If we add these up and we take the summation of these numbers over n, we're going to get something which is very close to the expected value of g of x, which using our dual notation is the same as this. So this is exactly the law of large numbers, because in essence, we can talk about this as our random variable, and we're just getting a new random variable, y is equal to g of x. And in order to get the expected value of y, we can go through the same mathematics that we did for the law of large numbers applied to y instead of x, and we get the expected value of g of x. So this is applicable, the law of large numbers is applicable to any sort of thing that you perform in terms of the function of the random variable. I guess I should make this a capital X here. So the law of large numbers is applicable here in any situation where you're taking the function of a random variable, and you want to estimate the expected value of that. That's the reason, for example, we can do y, or say z is equal to x squared, and we can sum the x squared and we get a good estimate of what? We get a good estimate of the second moment. And if we get an estimate of the second moment, we can use that to estimate the variance. That's what we get with the sample variance. So it's a very powerful, powerful result. And it is not just limited to the average. It's limited to estimating any expected value that you have. And we are assured that in the limit, that these are, that this approaches, I shouldn't have an equal sign. I said, I should have, this approaches as n goes to infinity, right? And this approaches as, or I'm sorry, this approaches, arrow going the wrong way. This summation over n approaches as n goes to infinity. So the law of large numbers is kind of cool. We can apply it everywhere. Okay, any questions at all? Uh-oh. I'm getting a bunch of pop-up things here that I don't want to deal with, but I had to, so that's life. Okay, let's talk now about some things that are going to tiptoe us into stochastic processes. Stochastic processes are, well, it's a situation where you have a random variable that's a function of time. Before we talk about this, we have to talk about sums of random variables and long-term averages, and something which is really kind of cool. I think that you are being presented here a couple of the most important theorems in mathematics. One is the law of large numbers. The other one is the central limit theorem. These are just astonishing results in mathematics, which have great application across the field of statistics and probability, if you will. Okay, we're going to prove now the central limit theorem. The central limit theorem, if you recall, says that if we sum up a bunch of random variables, that we know that we convolve their probability density functions. So if we have this convolve with this would be two random variables that would be uniform. We know that we get this, which is a triangle. That's everybody's first convolution, I think. And if we take this triangle and we convolve it with another uniform, so this would correspond to adding up three independent random variables, we get something which is piecewise quadratic. And already this is starting to look like a Gaussian. And the idea behind the central limit theorem is if you add up a number of random variables, and they don't have to be IID, they can be anything you want to, you will eventually get a random variable. In fact, it's really crazy. Suppose that you have just this crazy random variable that looks like this. So this is the density function, okay? I don't know what that loop is there, but you'll forgive me. And you convolve it with another density function that looks like this. And you convolve this with another density function that looks like, I don't know, it looks like something like this. Whoop, bloop. Okay, something strange. If you convolve all of these random variables together, you will get a Gaussian in the limit. It turns out the convolution, as you know, through experience, is a smoothing operator. If you convolve something with something else, it kind of smooths things out. Like down here, this has abrupt edges. These rectangles have abrupt edges, but this has no abrupt edges. And this idea of the piecewise quadratic is even smoother than the triangle. So every time you convolve, you get smoother and smoother and smoother. And the result is that eventually you get something which looks like a Gaussian. This is astonishing. I think it's an astonishing result, but one which is used in everywhere they use statistics, like in the social sciences and other places. So let's talk about the sum of NIID random variables. So this is the idea we're going to do. We're going to talk about the sum of x sub k. And one of the requirements, by the way, is that the central limit theorem is that it had a standard deviation that is less than infinity, and x bar is defined. And I guess, come to think of it, X bar must be less than infinity too. So you have to have a mean and a standard deviation for all your random variables to work. And you'll see that in our derivation, we assume that this is indeed the case. So let's go ahead and derive the central limit theorem. And we're going to start out with this summation. If you recall, what was the expected value of the summation? It was the same as the expected value of X. Notice here, I'm assuming IID. Now, what I told you was applicable to any random variable. You could sum a bunch of different random variables to different shapes. Here, all of the random variables are going to have the same shape. So if they're IID, then we've already shown that the expected value of S is equal to the expected value of the underlying random variable. And then we also showed that the variance of S was equal to the variance of X divided by N. That's the reason we can say as the average number of N as the number of values as N is increased, that this variance of S gets smaller and smaller and smaller and smaller and smaller and collapses the probability density function to be centered where X bar is. So we've talked about that already in the idea of the law of large numbers, and that the law of large numbers is applied to the sum approaching what we have. Now we're going to define Z is equal to S minus X bar over the standard deviation of S. Those of you in statistics have seen this before, where you take X is equal to Z is equal to your random variable minus X bar over the standard deviation. You should have seen this before, because this is a standard operation which is used in probability. Why are we going to do this? We're going to do this because both of these have the same mean. So the expected value of Z is equal to 0, since we're subtracting off the mean, and both this and this have the same expected value. The other thing is that the variance of Z is equal to 1. So by doing the Z operation, we're taking an arbitrary random variable, and we are reducing it to something which is a zero mean unit variant random variable. So that's our motivation for doing this. And now we're going to substitute this value. We know that the expected value of S is equal to N times this, and the standard deviation of S is equal to sigma times root N. Okay. Okay, why does that give me pause? Standard deviation of S. I think that's a typo there. I think this should be divided by, right? Because up here we have the variance of X over N. So that should be that. Okay, so the limit of the random variable Z, and here's the central limit theorem. The limit of the random variable of Z is equal to 1/2 plus the ERF. And this is what we're going to prove. We're going to prove that the cumulative distribution function for the random variable Z is the cumulative distribution function for the zero mean standard deviation Gaussian random variable. And if you recall, this is our definition of ERF, and we talked about this before and recognized that the MATLAB definition was a little bit different, and we actually had a homework problem associated with that. So what are some applications of the central limit theorem? We're going to look at some applications before we look at the proof. One of the things coming up is your income tax. I understand that income tax has been delayed until May this year. But anyway, if you go to the income tax guy and he enters your stuff in your column, enters dollar amounts, he can do one of two things. He can keep the dollar amount to the penny, or he can round it up or down to the nearest dollar. And that's an IRS rule because they're not interested in pennies. They're interested in making dollars. So if you have like $100.51, you can either enter it as $100.51, or you can round it up to $101. But the problem is you can't choose where you round and where you don't round. If you don't round, you don't round the whole form. If you round the whole form. So here's an example. What we're going to do is we are going to look at the sum of x's here, and these are going to be rounded out. These are going to be the rounding error in each case. In other words, if you round, you're going to make an error between minus $0.50 and $0.50, right? So the worst you can do if you round down is to round down to and lose $0.50, 50 cents. Or if you round up, you can at most make 50 cents. So this is the distribution of your rounding error. That's what X is. X is the rounding error. And you could lose, again, anyway from minus $0.50 all the way up to $1. And then if we have a bunch of n's in here and we round off, what's our total rounding error? Our total rounding error is the summation of the individual rounding errors, where an individual rounding error looks like this, is uniform. So we know kind of intuitively that the expected value of X, the rounding error, is 0. If it wasn't 0, the IRS wouldn't allow it. And I do know that the variance of X, take my word for it, the variance of this random variable is equal to 1/2 square dollars. I don't know what a square dollar is, but it's $1 squared. So this is equal to 1/12. So remember this, the mean is 0 and the variance is 1/12 of this result. So that means that the standard deviation of X is equal to 1 over root 12 in terms of dollars. So that's the standard deviation of this random variable. So the Gaussian random variable has two parameters. It has the mean and it has the standard deviation. According to the central limit theorem, if I add up n of these, then my S will be very, very close to Gaussian. And the cool thing about the Gaussian is the Gaussian only has two parameters. It only has the mean and it only has the standard deviation. If we know the mean of a Gaussian and the standard deviation of a Gaussian, go home. You have all the information you need to know. So if the central limit applies, it should have a mean of 0 according to here, and it should have a standard deviation or a summation of n over 12. I just remembered something, guys. This is right. It is times n because we're adding up the sum. The variance of S is not equal to that, it's equal to n. It's what I got goofed is that the average, here's where I goofed, and I'm sorry, the expected value of the average was equal to X bar, and the variance of the average was equal to the variance of X over n. So there's where I screwed up. I was screwing up my sums and my average. So sorry about that. And by the way, I've learned a long time ago not to question myself. I questioned myself here and I had it wrong. So that indeed was the correct answer. So sorry about that. So anyway, this is the probability density function for the sum of these random variables. So if we had n, which is the number of elements that we added up, this would be a Gaussian random variable centered at the origin with a standard deviation of root n over 12. And what happens if n increases? If n increases, this spreads out, right? It becomes more and more uncertain. Think about that. If you have a round off error and you have 10 numbers and you have round off error and you have 100 numbers, the standard deviation of the 100 numbers is going to be a lot larger than just the standard deviation of 10 numbers. So with this, we can ask all sorts of things. we can ask ourselves again, what's the probability that this sum, or what is n when the probability of the sum is greater than $100? So we can literally substitute in the value of n and get a 50-50 and say a 50-50 chance of that happening. Well, this leads us to this leads us to the central limit theorem, and we're going to apply the so-called Laplace-de Moivre theorem. The Laplace-de Moivre theorem is a special case of the central limit theorem. If you remember that this is a what? This is a binomial random variable. And you remember that the expected value of the binomial random variable was equal to NP, and that the variance of the variance of x, sorry about that, the variance of x is equal to NP times 1 minus P. So this is sigma. So what is the exponential? It's 1 over root 2 pi sigma. Looks like this should be a square root. I'm sorry, guys. 1 over root 2 pi sigma e to the minus x minus x bar squared divided by the variance of x. Or let me just put a sigma squared here. So this is the random variable. This is the Gaussian random variable. So if we substitute sigma here, which is NP1 minus P, there it goes, there it is. And if we substitute the mean here, which is NP, the mean is NP, and we substitute sigma squared here, we get, I'm sorry, this should be 2 sigma squared. Then we should get 2 NP times 1 minus P. So this is according to the central limit theorem, what the binomial should approach in terms of a Gaussian. And indeed, if you remember a long time ago when we talked about the binomial, we showed some curves and we showed, wow, it's really starting to look bell-shaped if we get more and more values of n. And so this is what it becomes. Now, this was discovered, I believe, before the central limit theorem and is referred to as the de Moivre-Laplace theorem, but it's a special case of the central limit theorem. So here is the astonishing result of the central limit theorem. We saw that, let's look at this. We saw that if S was binomial, that if we did a bunch of sums of it, it was still binomial, right? But now we said that this binomial, as n goes to infinity, becomes a Gaussian. And you remember the Poisson random variable stayed a Poisson random variable if we added a bunch of them together. And as n goes to infinity, that becomes a Gaussian. We also showed if S was gamma and the x sub k's are gamma, then if the random variables you're summing are random random variables, then S is a gamma random variable with a different parameter, of course. But now we've shown as n goes to infinity, it's a Gaussian. Everything goes to a Gaussian. If here's the same thing for the negative binomial, it goes to infinity, it's Gaussian. But we do have to be careful. Remember, we have to have defined means and standard deviations. So if x is Cauchy and the x sub k's are Cauchy, and you add a bunch of them, it's Cauchy. It doesn't go to a Gaussian. And this is something we showed also. A Cauchy never goes to a Gaussian. A Cauchy goes to a Cauchy. So to apply the central limit theorem, you have to have, again, a defined mean and a defined standard deviation. Okay. Let me check the time. Okay, the time, we're a little bit over time. So with that, let me ask and see if anybody has any questions.
Yeah.
Yeah.
Is there a general sense for how many of these different distributions you have to add before they start looking more and more Gaussian?
That's an excellent question. We do know that it works asymptotically. And in fact, I worked with a guy, published a couple papers with a guy that said, you know, all of these people in social sciences and stuff assume a Gaussian. You have a homework problem, which is the chi-squared, right? The chi-squared assumes a Gaussian, doesn't it? And it usually appeals to the central limit theorem to allow for that Gaussian assumption. But my friend Gary Wise said that no, that's not the case. Many times that the number of samples they use are too small in order to assume a Gaussian. And it's very case dependent. It's very case dependent. And is such a, but it's such a powerful result that people throw the result at a problem very, very quickly without a lot of thought and head scratching. Okay.
Cool. Thank you.
Okay. See, I think you can answer that question for specific distributions, but just in general, no, I don't think there's any one example. I suspect that you could probably construct a random variable that took, 1,000 iterations to resemble a Gaussian to some sufficient degree of accuracy. Okay, any other questions at all? Okay, hearing none, let's go ahead and call it a day, and I will stop sharing my screen. Yeah, let's call it a day.
Quick research question if you have a minute after this.
Okay, that sounds good. Okay, guys, we'll go ahead and stop. And if you want to hear Adam's research question, you can stay on. If you don't, you're welcome to log off. Oh, by the way, there's another eBears, isn't it? What time is that?
2:30.
2:30. Okay, I have some time then. Okay, guys, take care.